Hey guys, how you doing? So welcome to the third video in the series. So we're going to go into what chemical bonding actually is, and we'll actually introduce the first type of chemical bonding, which is ionic bonding. Okay, so let's jump into it. Okay, chemical bonding. So when it comes to atoms, the way that they interact with one another is predominantly determined by the electrons in the outer shell, which is what we call the valence electron. Basically, the chemical properties that you see, why is it that certain things, like for example hydrogen, burns so easily, its reactivity is actually determined by the number of electrons in their outer shell, which is the valence electrons. And in chemical reactions, we are predominantly interested in the electron. In acids and bases, we're interested in the proton. And then in something like nuclear reaction, where we're interested in the neutron. So for example, in nuclear fission, to get one atom to split into two atoms, you throw a neutron at it and it initiates a nuclear reaction. Okay, but in this particular case, for chemical reactions, we want to see how the electron plays a role in that interaction. Okay. And the way that atoms can interact with one another is in one of three different ways. Okay, so they can either lose the valence electrons and give it to another atom, it can take the valence electron from another atom, or it can share the valence electrons with the atom. That is, if you have two atoms, then the valence electron will share and orbit around both, okay, rather than just giving or just taking. All right. So when electrons from one atom interacts with electrons from another atom, that's what we call a chemical bond. Okay, and so a chemical bond really just represents that interaction between the electrons in the different atoms. Yeah. So for example, if you were to take something that has carbon in it and then you burnt it, the carbon reacts with oxygen in the air, which is why you need air or oxygen in order for a fire to maintain, and then it forms a chemical bond, forming something like carbon dioxide or carbon monoxide. Okay, so that's what we call a chemical bond. Now, the types of chemical bonding, there are three types of chemical bonds. The first is what we call an ionic bonding, which is the one we're going to take a look at in this video, where one atom will give its electron or electrons to another atom. In other words, one will give and one will take. A covalent bond, where two or more atoms will share their electrons with one another, the key word here being share. And the third one, metallic bonding, which we're not going to cover in this series, when multiple atoms will share a group of electrons called a sea of electrons. Okay. This table kind of summarizes it up. So if you have metallic bonding, the bonding will occur between a metal and another metal, okay? And the kind of distinction is that they will share a sea of electrons. If you have ionic bonding, you will have a metal share with a non-metal, where the metal gives and the non-metal takes. And that's what makes a metal, is that it gives. And that's what makes a non-metal, is that it takes. And then you've got covalent bonding, which is a non-metal and a non-metal joining together, where they both share the same electrons. Okay, and so these three types of bonding pretty much covers the entire periodic table. If you take one element, for example sodium, and you take another element, for example chlorine, right? Sodium is a metal and chlorine is a non-metal, and so which type of bonding do you think is going to occur between sodium and non-metal? It will be ionic bonding. Sodium and chlorine cannot bond together covalently because they are not two non-metals. They are a metal and a non-metal. If you take, for example, oxygen and then you join it together with carbon, for example, they are both non-metals, and so oxygen and carbon, which are both non-metals, must bond together in a covalent manner. They can't bond in a metallic way, which is between two metals. Okay, and so that's the key distinction there. We're going to introduce you guys to ionic bonding, which is the one we cover in the most depth, and also one of the ones that you probably sort of see with all the flashy chemical reactions and blah, blah, blah. Okay, so let's take a look. Let's start with an example atom. Yeah, so let's look at sodium. So if you pull up sodium on your periodic table, we're going to use sodium as an example of an atom that will lose electrons readily. Okay. The first and most important number you need to reference is the atomic number, because the atomic number will tell us the number of protons and the number of electrons. So as I'm going through this, you should be able to look at sodium, and go, okay, the atomic number is 11, therefore it has 11 protons, 11 electrons. And what we are interested in for ionic bonding is the valence electrons. If it has an atomic number of 11, you need to get to the electron configuration first, and then determine the valence electron, okay? Now, the electron configuration for sodium will be 2, 8, and 1, and that 1 that's right there, that's the valence electron, or the valency of sodium, which is 1, okay? So the valence electrons that it contains is 1. Now, what that means is that sodium actually has a choice. Because of the octet rule, atoms want 8 in their outer shell to be stable, with the exception of the first shell, right? And so sodium needs to get to 8. That 1 needs to turn into an 8, and it will do that by either gaining 7 more electrons to make it into an 8, or alternatively, what sodium can actually do is, because it only needs 8 in its outer shell, you can dump the outer shell that it has now by losing those electrons and going down a shell, reducing the number of shells it contains. So if it's 2, 8, 1, if you get rid of that 1, it will go down to 2 and 8 would make it stable. And so if it does this and it chooses to lose the 1 electron, it will become what we call an ion. It is no longer a sodium atom, it becomes a sodium ion. And this is what it looks like in its electron configuration. Na, 2, 8, and 1, that 1 will be thrown out. It won't just go and disappear into thin air, it will go to another atom that sodium will react with in an ionic way, okay? And then that loss of electron means it is now 2 and an 8, and it is called a sodium ion, okay? So the numbers have changed. Sodium is now called an ion. The atomic number is the same, but it has 11 protons, but only 10 electrons, which means its electron configuration is now 2, 8. Because it has 8 in its outer shell, it is now stable, and we now call it a positive ion because it has lost its electron, and the electrons are negative, and that is called a cation. And this is what sodium would now look like. You don't write it as Na, you would now write it as Na+, and that will be the ionic formula for sodium, okay? Now, this plus actually represents what we call the net charge of sodium, okay? It is a plus not because sodium has gained an electron or lost an electron. In fact, because it has lost an electron, you would think it would be a negative, but it's not. Because electrons are negatively charged, what that means is that if you lose an electron, you become more positive. Yeah, you've lost one of your negatively charged electron and have become more positive as a result of that. If sodium had 11 protons, that's 11 pluses, but only 10 minuses to counter it. So overall, it is more plus than it is minus, making it a positive ion, which we call a cation. Now, the way that I like to remember this is that a cation is positive because cats are positive, okay? And so that's what sodium ends up as, and you would write it as Na plus. Now, there's an invisible 1 there. It can actually be written as Na plus 1 or Na1 plus. It doesn't matter where the number goes, but we leave it invisible because it's only 1. If, for some odd reason, I'm going to make it up, sodium loses 2 electrons, it will be Na2 plus or Na plus 2, right? Showing exactly what the overall charge is. It's because it's lost 2 of its electron, it has become 2 times more, so not 2 times, 2 positive overall charge. Okay, so its net charge will be 2 positive, but it doesn't do that. Sodium only loses 1 because it only needs to lose 1 in order to become stable. Okay, now if we look at the other end of the spectrum and we look at another atom, for example, like chlorine. Chlorine is an example of an atom that wants to gain electrons. If you look for chlorine in your periodic table, its atomic number, the first number you should be referring to, would be 17. Based on that, number of protons, also 17, number of electrons, 17, and the electron configuration, following the octet rule, 2, 8, 8, 8, would be 2, 8, and then 7 in its outer shell, making 7 its valence electron number. Okay, now that 7 means that chlorine will either need to dump all 7 electrons or gain one more electron to become stable because of the octet rule. And when it does that, it also becomes an ion, but it becomes a different type of ion. Here's a diagram of what it looks like, okay? Chlorine originally looks like this, a chlorine atom, 2, 8, 8, and then 7 with that missing electron there. It's going to gain an electron from another atom, and if it does that, it becomes 2, 8, 8, yeah, in its outer shell, and it is now a chlorine ion. You don't call it a chlorine atom, you call it a chlorine ion. It has a new number of electrons, 18 electrons, 17 protons. It has a new electron configuration, 288, and because it has 8, it is stable. And because it has gained an electron, it has gained a negative charge, it is overall a negative ion called an anion, and it looks like that. Okay, its net charge being negative or -1 or 1 negative. And the way I remember this is that anion sounds like onions, and onions are negative. Okay, so that's chlorine and that's sodium. So let's put the 2 and 2 together and figure out how do we know which one's going to lose and which one's going to gain. If you look at the periodic table, every element will either lose or gain unless it is the noble gases, which will do neither because it's already stable. And in some cases, elements in group 4, if you think of it as a spectrum, 8 is your goal, right? And if you get to 0, you go down a shell and you get to 8 anyway. So it's quite simple if you think about it. Then the midpoint will determine what the pattern is. So anything less than half is going to lose it. It's going to dump it because it's energetically easier for sodium to lose its electron, and energetically easier for an atom with only 1 to 3 valence electron to lose, and it's energetically easier for an atom with 5 to 7 valence electrons to gain. Okay, and so that's the pattern that we follow, and you can determine their numbers based on that pattern. All right, and we're going to keep using that as a reference. If it has 8, it doesn't do either. It won't lose and it won't gain, which is why something like helium won't lose or gain electrons from other atoms because it already has all the electron it needs to be stable. Okay. If it has 4, it can either lose or gain. It can do both, right? And so if it's 1 to 3, it will lose. 5 to 7 will gain. 8 won't do either, and 4 will do both. Or in some cases, 4 actually will also do covalent bonding, which is the other type of bonding, which we're going to cover in the next video. Okay, so let's put 2 and 2 together. Now, cations tend to give their electrons to anions to form that ionic bond, right? It's an ionic bond because you must have one that is giving and one that is taking, and they join together. So for example, let's put our 2 together, right? Your sodium atom there overall gives away 1 electron. Your chlorine atom here, or your chlorine ion, will take 1 electron. When that happens, sodium becomes a cation, positive, giving its electron to chlorine, and chlorine becomes an anion, negative. Now, because sodium is now stable, but it has a net positive charge, and chlorine is also stable, but has a net negative charge, the plus and the minus are attracted to one another, and so they join together because of that positive negative charge, right? So what you end up with is the sodium and the chlorine join together, and it forms sodium chloride, which happens to be table salt. So the stuff that you sprinkle on your steak and your chips and stuff like that, that's actually sodium chloride, table salt. And this is what 1 grain would look like. A lattice of chlorine and sodium joined together in these kind of interwoven grids, okay? And we represent that with an equation. Yeah, the sodium ion symbol or formula, Na plus or Na plus 1, will join together with Cl minus or Cl minus 1 to form NaCl, which is now neutral. It's stable. So that plus and minus cancel each other out, and you end up with just NaCl, which is joined together and stable. Yeah. Now, if you remember in video 1, you will remember that this lowercase really matters, because when multiple atoms join together, we rely on differentiating this lowercase from a capital, okay? So N capital and lowercase a tells us that it's a sodium atom. C capital lowercase l will tell us that it's chlorine. And so NaCl would tell us that's sodium chloride, okay? So the ionic bond, you end up with now no longer an atom, but you call it a compound. And because a compound is a combination of two or more different elements held together by ionic bonding. Okay, so in this particular case, NaCl is what we call an ionic compound. When you have multiple compounds joined together, it forms a lattice, like a grid, just like in Lego blocks. If you have multiple Legos stacked on top of each other like that, you form a lattice of Lego. In this case, you form a lattice of ionic compounds, and it's a regular arrangement in large structure. 1 grain of table salt will have millions of these lattices of ionic compounds joined together, and that's what it looks like there. Okay, all right, we're going to get you guys practicing with magnesium and chlorine. So in this second example, what I actually want you guys to do is do a bit of note taking, and I want you to draw up this table into your books or your notes, and just hit pause on this video, draw it up, and start practicing, because this will help you go through the process as to how do we determine what type of ion it's going to become, and how do we write out that chemical equation that I just wrote out in the last one, so that you guys become confident in determining what does what. Okay, so draw out that table, and then I'm going to start showing you how to fill it out. Okay, so we're going to use a different example. We're going to use magnesium, which has an atomic number of 12, and chlorine, the same one, has an atomic number of 17, a more complex example, but that'll hopefully bring the example home a bit better for you to understand. Okay, so let's start with magnesium. Okay, magnesium has an atomic number of 12, and the first thing I want you to be able to figure out, using your knowledge from the first video, is what is the electron configuration of magnesium. Okay, you can draw it out following the octet rule: 2 in the first row, also 2 in the first shell, and then 8 in every other shell, and you should be able to get to this configuration here: 2, 8, 2. When you get the electron configuration number, you can determine how many electrons sit in its outer shell simply by looking at that last number on the right there. Yeah, so here, 2. Magnesium has 2 in its outer shell. Draw it out if you are not sure, but that means that its valence electron will be 2. Okay, it has 2 valence electron, and from there, you need to determine, okay, if it has 2 in its outer shell, what is it going to do? Is it going to lose or gain, or neither, or both, right? And to do that, we use the little table that we referenced before, and here's a little short to keep you to keep reference for you. If it has 1 to 3 electron, it must give it away. If it has 5 to 7, it must take it. Okay, remember that give means it loses the electrons and becomes more positive. Takes means it gains an electron and becomes more negative. Okay, so magnesium has 2 electrons, not 1, and what it will do is, because it has 2, it will give those 2 electrons, which means its net charge will be 2 plus. Yeah, plus, because it has given away the electrons which are negative, right? And so Mg, and because it has 2 electrons, it's going to give 2 electrons away to form an overall net charge of 2 plus, and so we write it as Mg 2 plus, or Mg plus 2. Okay, because it is positive, it is a cat. Cats are positive, it is a cat ion. Okay, try and do the same for chlorine. Right, chlorine has an atomic number of 17. Its configuration will be 2, 8, 7, meaning that its valence electron will be 7 in its outer shell. If it has 7, it is going to want to take. How many does it need to take to get to 8, which is the stable number? Well, it needs to take 1 electron, meaning that it becomes 1 minus, because when it takes the electron, it becomes more negative. Okay, therefore you write it as Cl1 minus, or just Cl minus, it doesn't matter. And because it is minus, it becomes an anion, because an anion sounds like an onion, and onions are negative. Okay, that's how you fill out that table, and ideally you should be confidently doing this with every element on your periodic table. Okay, now before I continue, I'm going to hit pause there, and I'm going to show you guys a bit of a trick of the trade that if you've been following these videos, you sort of now will be able to pick up. Okay, back in the previous video when we looked at periodic trends, I mentioned to you that the group number will tell you how many valence electrons sits in its outer shell. Okay, so the group number is the number that sits on top of each column, right? Ignoring the transition metals that I told you guys to ignore, right? If you look at magnesium, magnesium has a group number of 2, okay? What that tells you is that magnesium has a valence electrons of 2, right? If you look at chlorine, chlorine is in group number 7 and therefore has 7 valence electron. If you know that, simply by looking at the group number, you can determine its valence electrons for every element, with the exception of the transition metals. They don't work with this model that we're following here. Okay, so for example, if you look at your periodic table right now and you look at, for example, oxygen, you will see that oxygen sits under group number 6 and will have 6 electrons in its outer shell, a valence electron number of 6. If you look at beryllium, beryllium will have 3? 3. It'll be in group number 3, and therefore it will have 3 electrons in its outer shell. Okay, was it 3 or 2? Possibly 2. My bad. My memory of the periodic table is not that awesome. Okay, if you go to iodine, iodine is in group number 7 and it will have 7 valence electron. If you know that and you know how to use your periodic table effectively, you can skip this electron configuration business and go straight to the valence number. Once you have the valence number, you can determine the net charge by looking at this little graph here, whether it gives or takes and by how much. You can write down the ion. Yeah, this net charge just attaches to the end to form the ion with the chemical formula, and whether it's a cation or an anion. And you can figure out now your chemical equation. What is magnesium going to do when it comes in contact with chlorine? Well, it's going to want to give 2 of its electron away to the chlorine, and chlorine is going to take 1 electron from magnesium. Okay, so this is what your chemical equation looks like. Mg, this one here, the ion number, or the ion formula, 2 plus Cl minus, I've just written the minus instead of the 1 minus, forms MgCl, which is now stable and joined together ionically, right? Now, you will notice this equation looks really different from the sodium one, because sodium is Na plus Cl minus NaCl. This one is Mg2 plus Cl minus MgCl. There is something wrong with this equation if you leave it the way that it is. And the reason for that is because the net charge of this particular equation is not 0. And that's a problem, because if it's not 0, it tells you that the atoms in there are not stable. They haven't gained or lost all of the electrons that it needs. And it makes sense if you think about it. Magnesium needs to give away 2 electrons, but chlorine can only take 1 before it becomes stable. And so chlorine will take its 1 electron and become stable, but magnesium is still unstable with only 1 chlorine atom, right? And so what actually happens is, in nature, you never get 1 magnesium atom joining with 1 chlorine atom. You have a whole bunch of magnesium atoms joining together with a whole bunch of chlorine atoms. And so what's going to happen is, magnesium is going to give 2 away, but 1 chlorine atom can only take 1 electron. So what actually happens is, magnesium has the spare electron that it will now give away to another chlorine atom, right? And so the balanced chemical equation will look like this. 1 magnesium atom will give to 2 chlorine atoms to form magnesium chloride with a small 2, signifying that for each magnesium there is 2 chlorine joined to it. Okay, so this big number is what we call the coefficient number, and this little number is the number of atoms within 1 compound. The coefficient tells you how many compounds there are, in this case 2 chlorines, and this little number tells you how many chlorine for each magnesium you have. Okay, so let's take a look at magnesium chloride. It's actually the same types of salt that we use for bath salts and things like that, and we actually use it also to melt like street ice and stuff like that in places like Canada and Russia and blah blah blah. Okay, this is what it looks like. 1 magnesium will join together. This is a very stick diagram to show that, together with not 1 but 2 chlorine atoms, giving 1 electron to this guy, which makes him stable, giving the other electron to this guy, making him stable, and that's what it looks like in diagram form. Yeah, Mg has thrown away 2 electrons and become more positive, Mg2 plus, with a 2 and an 8 electron configuration. Each chlorine has 2, 8, 8 in its outer shell, taking one from magnesium on one side and the other electron from the other side, and now these 3 join together to form MgCl2. Okay, so that's how you work out what happens. So give it a go. Pick a few metals and a non-metal and join them together and see if you can try and put them together based on that. Okay, you will notice the second thing, which is the name change. Okay, when you put atoms together to form compounds, the name naturally always changes. You don't get, when you put sodium and chlorine together, you don't form sodium chlorine, you form sodium chloride. When you put magnesium chlorine together, you get magnesium chloride. So when it comes to ionic compound, the first word, which is the metal, the cation, stays the same. That doesn't change. However, the suffix of the second word, the anion, is dropped in favor of an IDE. Okay, so instead of chlorine INE, it becomes chloride IDE. If it was fluorine, it becomes fluoride. If it was iodine, it becomes iodide. It's not as simple as just an IDE, drop the last 3 letters, add the 3 last letters in. For example, oxygen, it would become oxide. So you drop the igen and put an IDE in. If it was nitrogen, it will be nitride, right? And so it's one of those things where you just have to remember it. As you encounter it more often, you'll start to remember that, oh yeah, oxygen becomes oxide all the time, nitrogen becomes nitride, and so forth and so forth. Okay. Now, finally, we're going to take a look at some of the properties of these ionic compounds. Okay, and there are 3 properties that I'm going to outline. The first is that ionic compounds tend to be very conductive of electricity in liquids. The second is that they have a high melting and boiling point. And the third is they are brittle and they will break easily under force. Okay. Now, the first one, it's conductive in liquids. Not many people know this, right? But one of the commonly known facts is that water conducts electricity. In truth, it is not water, the H2O itself, that conducts electricity. It is the dissolved ions of an ionic compound that conducts electricity. Yeah. When you put salt in water and you mix it, right, it dissolves. The reason why it dissolves is because the Na plus of sodium chloride and the Cl minus separate in the water, and it's the Cl, the minus in the Cl, that conducts electricity. It allows electrons to flow through it, meaning that when you put electrical charge through it, it will transfer through the liquid because of the dissolved ions, and it will come out the other side, right? And your body conducts electricity because your blood and the water in your blood contains heaps of dissolved metals and ions that allows it to then conduct electricity. Okay, and you can test this because if you take pure water, pure H2O, evaporated water, recollect it back down into a liquid, that water won't conduct electricity, right? Ionic compounds also have a high melting and boiling point. It takes a really high amount of heat, about 1,400 degrees, to melt glass, because glass is an ionic compound. If you put salt in a frying pan, you're not going to melt the salt as easily as you would, for example, sugar, which is a covalent bonding molecule, because salt has a high melting and boiling point. Whoops. And so the ionic compounds tend to have a really high melting and boiling point. Now, this high melting and boiling point doesn't mean that it's that tough. It actually is really brittle. If I take a hammer and I hit glass with it, glass is actually silicon oxide, which is an ionic compound, silicon and oxygen joined together, but it's brittle. And the reason why it's brittle is because of the way that it's structured. See the plus and minus that we were talking about before? The anion and the cation at the moment are really strong because they're next to each other, right? A negative and a positive next to each other will be really good, but a negative next to a negative, for example, here and here, or positive next to a positive, will repel one another. So if I take a hammer and I add just a bit of force and I misalign that lattice just a little bit, and I get the plus in next to another plus, they're going to repel each other. And because they're going to repel each other, you're going to get a shattering of the ionic compound. Whether it is salt or whether it is glass, it will shatter because the repelling of the plus and the minus from one another, and you get a crack in the crystal as a result of that. Okay, and so that are some of the properties of the ionic compound. And that's it for this video. Next video, we're going to take a look at covalent bonding, and we're going to finish off the chemistry series by looking at a different method in which chemicals can, elements can chemically bond with one another. I'll catch you guys then.